section 5.3 diagonalization. This is the last section of our course, so hopefully you guys should be okay with this. So recall from section 5.2 that two square matrices are called similar when there exists an invertible matrix P such that B is equal to P inverse AP. So the two matrices probably are A and B. So they are similar if we can find a matrix P and can write them like this. Or A equals P inverse B. Now it doesn't have to be, the name can be different. So we can have A equals Q inverse B Q. Format is the same. So matrices that are similar to diagonal matrices are called diagonalizable. An n by n matrix A is diagonalizable when A is similar to a diagonal matrix. That is, A is diagonalizable if there exists an invertible matrix P such that P inverse AP is a diagonal matrix. So there is a theorem here, an n by n matrix A, theorem 5. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. So because we have the size of A is n, so we must have n linearly independent vectors, eigenvectors. In other words, A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. And such basis is called an eigenvector basis of Rn. Theorem 6. An n by n matrix with n distinct eigenvalues is diagonalizable. So if the matrix has n distinct eigenvalues, then it will have, for each eigenvalue, you will get one eigenvector. So there will be n eigenvectors which are linearly independent, so they can form a basis for the Rn. So let's look at an example. How do we diagonalize a matrix, or how can we find this P and D matrices? So the matrix A is given here, and two of its eigenvalues are also given. The eigenvalues are 2 and 3. Is A diagonalizable? Question. If so, find P and D so that A is equal to P D P inverse. Let's see. I have rewritten our matrix is, we are going to look at example 1. So matrix is A equals two 0 minus 2 1 3 2 and 0 0 3, and lambda equals 2 and 3. So one lambda is 2, the lambda is 3. So when lambda is equal to 2, so we are trying to find the eigenvectors associated with lambda is equal to 2. So remember, this will give us A minus 2i. So A is this matrix that you see here, 2 0 negative 2 1 3 2 0 0 3 minus 2 twice the identity matrix. So identity matrix has non-zero entries on the diagonal. Each entry is 1. So when we multiply it by 2, we get 2, 0, 0, 0, 2, 0, 0, 0, 2. And now carefully subtract the 2. So 2 minus 2, first entry of both matrices is 2, so we get a 0 in that place. Then we have 0 minus 0, which is 0. Then we have negative 1 minus 0, negative 1. Second row, 1 minus 0 is 1, 3 minus 2 is 1, 2 minus 0 is 2. And the last row, third row, 0 minus 0, 0 minus 0, and then 3 minus 2. So now we say that, so basically we are going to solve this equation a minus 2ix equal to 0. Remember how do we do that? We take this matrix which is a minus 2i here that we found, and we augment the 0 vector with it, and then we do our row operations. This is our matrix, and augment the 0 vector. Now do the row operations. The first one is to swap the rows because we need a 1 in the first pivot position, so we do R1 swapped with R2. So this gives us 1, 1, 2, 0, and then 0, 0, negative 1, 0, and the last one is 0, 0, 1, 0. So you can see there is pivot in the first column and the last column. So x2 variable is column 2 is gives us a free variable. So we can multiply by negative 1 the second row, or maybe we should first use it as it is with the to make the 1 under the pivot to be 0. So I do R3 plus R2, and also I want to make this quantity a 0, so I need negative 2R3 plus R2 R1, which gives us the first row becomes 1, 1, 0. Second row becomes 0, 0, 0, and the last row 0, 0, 1. So we have a row of zeros. We have to shift it, swap it, and get it to the bottom. So we swap second and the third row to get 1, 1, 0, 0, 0, 1, and then 0, 0, 0, 0. So now notice here This is x1, this is x2, this is x3. So there is a pivot in for x1 and pivot for x3, which means this is a free variable. So x2 is the free variable. So writing our equation from first row, we get x2. This was a pivot, there is a 1 here. Okay, so we have 1, 1, 0, the first row, which gives us x1 plus x2 equals 0. X1 plus x2 equals 0, which gives us x1 equal to negative x2. And then we have nothing else. So why? Because x2 is free and x3 is 0. By reading this last row, you should be able to figure that out. So 0. So x3 is 0. So what will the vector look like? So we'll say let x2 equals to t, then x1 will be equal to negative t, x2 is t, and x3 is 0. So that our x is negative t, t, 0. And we can pull out the t and we get negative 1, 1, 0. So this is our the eigenvector associated with the lambda is equal to 2. Now we try to find the other eigenvector which is associated with lambda equal to 3. Eigenvector of A corresponding to or related to or associated with lambda is equal to 2 is negative 1, 1, 0. Now what about lambda is equal to 3? So we have to repeat the process. So when lambda is equal to 3, what we will find is a minus 3i. A minus 3i, that's what we are looking for. And a is A is 2, 0, -2, 1, 3, 2, 0, 0, 3. Minus 3i means 3, 0, 0, 0, 3, 0, 0, 0, 3, which gives us, so the first item or entry in the first row and first column, we have 2 and -3, so we get a -1. In the first row, second entry will be 0, and the third entry will be -2. So -2 minus 0 is -2. So second row, we will have 1, 3 minus 3 is 0, and then 2 minus 0 is, and then last one will be 0, 0, 0. So now remember, like before, we take this matrix -1, 0, -2, 1, 0, 2, and 0, 0, 0, and we augment the 0 vector. And now we do the row operations, not too many to be done here. You can see what happens when we try to eliminate the one in the second row using the top row. So we add row 1 to row 2, and we end up getting -1, 0, -2, and then 0, 0, 0, 0, 0, 0, and 0, 0, 0. So now notice here, there is only one pivot, and we can multiply by -1. So to get, so I'll multiply the first row by -1. So we end up getting 1, 0, 2, 0, 0, 0, 0, 0, 0, and the augmented vector. So this is telling us that we have pivot in only one column, so we have free variables x2 and x3. So x2 and x3 are free variables. Remember, the others which are not free are called basic variables. So I will at this moment let x2 is equal to s and x3 equals t. Doesn't matter, you can call t x3t as s and t x2 as t. So now from the top we have, from the first line, we have x1 plus 2x3 equal to 0, or x1 equals -2x3, which is equal to -2t. So now we have our x vector. So x1 is -2t, x2 is s, and x3 is t. So notice there are there were two free variables, so we are getting two eigenvectors. If one we can write s The one with S will be 0, 1, 0, and the one with the T will be plus T times negative 2, 0, 1. So these are the eigenvectors of A corresponding to lambda equal to 3. Okay. So now, in order to check whether what is the D and what is the P in this problem, matrix D and the matrix P. So the eigenvalues form the D vector, and all these three vectors combined, these two are definitely linearly independent. You can check by inspection, because one is they are not scalar multiples of each other, but also you can check independence of all three. The ones that was for 2 and lambda equal to 2, and these two vectors which are eigenvectors for lambda equal to 3. So once you have checked the linear independence, now we can form them, the D and the P. So the D matrix will contain the eigen values along the diagonal, and there were only 2 eigenvalues given, but the dimension of the eigenspace for lambda equal to 3 is 2. So 2 has multiplicity 2. Sorry, 3 has multiplicity 2. So 3 has so 3 will come twice. So we can write as 2, 0, 0, 0, 2, 0, sorry, 0, 3, 0. Because 2 is appearing only 1, 2 has multiplicity 1, 0, 0, 3. And now we should write P. P contains the eigenvectors, but corresponding eigenvectors. The first column was the eigenvector for 2. So the eigenvalue for 2. So now we have to write the eigenvector that we've got for lambda is equal to 2 in the first column. So it will be negative 1, 1, 0. And these two vectors that we have, 0, 1, 0, negative 2, 0, 1. So that will be our P. So we say A is diagonalizable. And we can also say A is equal to P A P inverse, P D P inverse. And we can check. Now to check, don't multiply 3. We don't need to multiply these three matrices, because if under to multiply, I will have to do the inverse of P, which is going to be could be long, too much work. So what we check here instead, check that AP is equal to PD. That's what we will check. So what is AP? A was 20 minus 2. 132 003, and we have our P negative 110 010 negative 2 0 1, which is going to give me, so negative 2 then we have 0, then we have again negative 2, negative 4 minus minus 2, so negative 6, and negative 1 plus 3 will be 2, and then 3, and then minus 2 plus 2 0, and then from the last one we get 0 0 3, and we now check PD. So how did I came about checking AP? You can see if I multiply by P on both sides, so it will be right multiplication, right, and the P will come on the right. So that's what we had, and from here this becomes PD because P inverse and P give us the identity. So now we want to check that PD is the same. It gives us the same as what we got for AP. So P is and D is 2 0 0 0 3 0 0 0 3. Minus 2, then we get 0, minus 6, and then the second row gives me 2, 3, and 0, and the last row 0 0 3. So we have the same matrices. Okay, so I will stop here and we'll do this second example in the next video.